going to begin by looking at examples, and then we'll try to develop the property after we've seen some examples. Beginning here, we're going to work on log base 4 of 2 plus log base 4 of 32. Now, I know that 2 is the square root of 4, so I can rewrite 2 as 4 to the power of 1/2. And that's going to let me solve for this left-sided log. I know then that this is going to be 1/2. So what we really have to do next is figure out how we can express 32 using a base of 4. Well, let's think about it using a diagram. Beginning at step 0, we start at 1, and we're multiplying here by 4s, so we get 4, 16, and 64 at steps 1, 2, and 3. Each of these segments can be broken down into 2 equal segments where we multiply by 2, because 2 times 2 is 4. So each of these segments here and here we can think of as multiplication by 2's, same here and here. Now what values am I going to have in these particular segments? Well, I should get 2, 4, then 8, then 16, and then 32. So if we want to get 32 as a base of 4, we need to figure out where this is. This is between 2 and 3, halfway. So we could say that 32 must be 4 to the power of 2.5. 2.5 we can write as 5 over 2. Now that the base of the logarithm and the base of our exponential expression are the same, I know that the numerical answer here must be 5 over 2. And when I add these two final fractions together, we get 6 over 2, which is equal to 3. Now I want to show this one more time down here at the bottom. We're going to evaluate log base 4 of 2 times 32. Now this is going to equal log base 4 of 64, and we can easily see from our picture that this is at step 3. So we could write 64 as 4 to the power of 3, in which case we have a numerical answer of 3. So look at what I'm trying to say here. I'm trying to say that if we have the same base of our logarithm and we're separated by a plus sign, we can take the two inner numbers and multiply them together to help us simplify our answer a little bit faster. This leads us to our first major property of logarithms, and that is the multiplication addition property of logarithms, or the MA property. The idea is if we have a logarithm with a particular base, let's call the base m, and we have two expressions on the inside that are multiplied together, so here capital A and capital B are any expressions, then we can change this into an addition. Logarithm base m of the first expression plus logarithm base m of the second expression. And of course this works in the reverse direction too. That is, if we start with the addition, we can combine it into one single logarithm with the same base where those expressions are multiplied together. Now the motivating fact for the MA property of logarithms is the idea that when we multiply like bases together, we add the exponents. So here, if we start with two expressions that are multiplied together with our base m logarithm, let's say that we can write a and b as some power of m. So m to the x and m to the y. Well, using our properties of like bases here, we can add our powers together to get m to the x plus y. And now that our logarithm and our exponential expression have the same base, we can note that this is just going to be equal to x plus y. Similarly, if we start with this side of the equal sign and we write a as m to the x again and b as m to the y, well then our first logarithm here we can rewrite as just the number x because we already have the same base. And our second logarithm similarly is just going to be written as y, so we have x plus y. Let's take a look at another example. In this case, we're going to look at our log terms and we're going to do a subtraction instead of an addition. So I've used the same logs, the same bases, and the same inside numbers as the last example. so that we can more quickly go through this example. So we know that 32 can be expressed as 4 to the 5 over 2, and we know that 2 can be expressed as 4 to the 1/2. So this implies that since we have the same base of our exponential expression as well as our logarithm, we're going to get 5 over 2 here and 1 over 2 here. And when we subtract these two fractions, we are going to get 4 over 2, or just 2. Now I want to compare this answer with what we'll get by taking the two inside numbers, 32 and 2, and performing a division. So in this case, this will come out to be log base 4. 32 divided by 2 is 16, and we can write 16 as 4 squared. Once again, the base of our logarithm and the base of our exponential function are the same, so we can evaluate this just to be the number 2. And once again, we notice that our final answers are similar. The nice thing about the example we did on the last slide is it does generalize to the following property. I call this the division-subtraction property, or the DS property of logarithms. The idea is if we have two expressions on the inside of our logarithm, so let's say we have two expressions, capital A and capital B, we can break this apart into two logarithms that have the same base. Here the base is m, and on the inside of these logarithms are those two original expressions, capital A and capital B. Because we're dividing on the inside, this turns into subtraction of these two logarithms on the outside. Of course, this does work in the reverse direction as well. That is, if we start with two expressions that are subtracted and we have the same base, those expressions on the inside will turn into division of one single logarithm. And the motivation for this, again, is similar to what we saw for the MA property. That is, if we think of A and B as powers of m, then division of these powers leads us to subtraction of the exponents. So I've summed up that idea down here below. And I have one final property that I want to introduce, and this one has to deal with moving powers around of the number on the inside of our logarithm. We're going to begin by evaluating 6 times log base 4 of 2. So once more, I'm going to leave the 6 on the outside here, because I'm going to multiply whatever answer I get from my logarithm by 6 in this case, and we're going to replace our 2 with a 4 to the 1/2. Now next we can replace this expression, log base 4, 4 to the 1/2, by the number 1/2. And 6 times 1/2 is equal to 3. Next, let's evaluate log base 4 of 2 to the power of 6. This is equal to log base 4 of the number 64, which is the same thing as 4 cubed. Now that my base of my exponential expression as well as my logarithm are equal, I know that this must be equal to 3. So notice here again we get the same final numerical answer. One way we have the 6 on the outside of our logarithm, and the other way we have it as an exponent of our exponential expression. Here's the third and final special property that I want to give you in this lesson, and that is the power property of logarithms. Here's the idea. If I have an expression inside of my logarithm that's raised to a particular power, then I am allowed to take that power and bring it down and multiply it on the outside of my logarithm. This also works in the reverse direction. If I have a number that's multiplied by a logarithm, I can take that number and put it as the exponent of the inside expression. Let's use the three properties that we've just seen to evaluate the following two expressions. The first one is log base 4 of 80 minus log base 4 of 5. Now here we can use the DS rule, the division-subtraction rule for logarithms. We have two logarithms with the same base, and they're separated by a subtraction sign, so this means we can take the insides and rewrite this as log base 4, 80 divided by 5. And 80 divided by 5 is 16. And then we can rewrite 16 as 4 squared. So now the log's base as well as the base of the exponential expression are the same, so this will evaluate to the number 2. Next up we have log base 10 of 100 to the power of 55. Now there's a couple different ways we could go about doing this question. I'll show you the way of using the power law for logarithms. So the idea here is, since we have this power on the expression that's on the inside, we can take that power and we can move it down in front of our logarithm like this. So 55 times log base 10 of 100. Now we can write 100 as 10 squared. And now the base of our logarithm as well as the base of our exponential expression are the same, so we get 55 times 2 for 110. It turns out that these three special properties of combining and expanding logarithms are very, very useful when it comes to certain calculus expressions. So we're going to work through a couple examples together on expanding and combining logarithms using these three properties. Let's use the laws of logarithms to expand the following two expressions. Let's begin with ln of x squared over y times z plus 1. Now, because we have two expressions that are divided here, we can break this up into two natural logarithms that are separated by a minus sign. So in this case, we can say ln of x squared minus ln of our denominator, which is y times z plus 1. And from here we can go on and do one more step. I am going to bring the squared power down out front so that we have 2 ln of x. And then I'm going to go ahead and break apart this multiplication. So we can break apart this multiplication into an addition to get ln of y plus ln of z plus 1. Now, of course, our last step here is just to expand our negative through, and our final answer here is 2 ln of x minus ln of y, ln of z plus 1. Next up, let's look at log base 10 of the square root of x minus 1 over x plus 1. Now what we need to do first here is get rid of that square root. So let's write this as log base 10 of x minus 1 over x plus 1, all raised to the power of 1/2. Now that we've done this, we can take this power and bring it down out front of our logarithm to get 1/2 log base 10 of x minus 1 over x plus 1. Now we have a logarithm where we have division on the inside. That means we can expand this into subtraction on the outside. So we have 1/2 log base 10 of x minus 1 subtract log base 10 of x plus 1. And our last step here is to distribute the 1/2 through, and we will get 1/2 log x minus 1 minus 1/2 log x plus 1. In this example, let's use logarithm rules to combine the following three expressions into one logarithm. What we want to do first is we want to see if there are any logarithms that are multiplied by a number out front. Because in order for us to combine into one logarithm, I can't use the addition property here unless these numbers are put back into the powers of our exponential expressions. So that's always the first step here. So I'm going to take that 3 and I'm going to put that inside as the power of x, and I'm also going to take this 2 and I'm going to raise x squared plus 3 to the power of 2 here. Now that I've gotten rid of those constants that are multiplied out front, now I can apply my addition and subtraction logarithm laws. Let's first begin with the addition. This addition is going to turn into multiplication on the inside. So we get 5x cubed on the inside. And now we can look at our subtraction. Our subtraction on the outside will turn into division on the inside. So altogether we should have ln of 5x cubed divided by x squared plus 3 all squared. Alright, my little epsilons, stay positive.